Okay, so in today's video, we're gonna do three things. First, to consolidate the knowledge that we got in the previous video, we're gonna start doing one more example for solving an exact equation. Then we're gonna consider a complication over the exact equations that we've seen in the previous video, which is equations that require integrating factors to be exact. And then we're gonna see examples of exact equations that require integrating factors. So it's gonna be a relatively intense video. Let's take it step by step, all right? To begin with, let's begin with the example to repeat and consolidate the knowledge that we got in the previous video. So we have the following problem. Find the general solution of this equation. As you can see, what kind of equation is this? Well, this equation, if you look at it, you see that this equation is actually, well, it's an ODE, of course. The dependent variable is y, the independent variable is x, and then you actually see, if you ask, okay, let's classify, is it linear? The answer is, yes, it is. It's linear. Look, all the powers of the maximum power of y, I mean the function that dependence on y is always through factors that are proportional to y and its derivatives. It's linear. It's a linear equation. In fact, to solve this, we're going to see a much easier way to solve it when we specialize on linear equations, which we will do in future videos. But it is also exact, perhaps. Well, I don't want to break the mystery. We're going to try to solve it using the methods that we learned to solve exact equations. Now, don't get fooled by the log and by the x squared. That is the independent variable. So that dependence on it doesn't make it nonlinear. Okay, remember that. That's important. All right, the first thing to realize is that, of course, y dot is dy dx, all right? Which means that, again, expanding the differentials properly, or, again, doing this computational trick that we know is not rigorous, right? And then you have to tell pure mathematicians to look the other way, but it gives you the right result applied algorithmically and knowing what you're doing, of course. Dx dy, you can put this on the right, you have the di on the right, and then you put back the term in here with the dx. We can write, in other words, we can write this as a differential form. Let's write it as a differential form explicitly. So a differential form equated to 0. So if we write it like that, this is 2x, well, I write it here, 2xy divided by x squared plus 1 minus 2x multiplied by dx plus, and then I'm going to change the sign inside and outside. This is the log of x squared plus 1, right, minus 2 dy, and of course equals 0. All right, so that is the equation we want to solve, written as a differential form equated to 0. Now the question that we ask is, well, is this thing a function? Is this thing the differential of a function? Or is this thing not the differential of a function? Because if it is the differential of a function, then I know that what the solution is. Right, the question, is this an exact equation? Or in other words, is there an f of xy such that df equals 0? Let's call this equation 1, such that equation 1 can be written as the differential of a function equated to 0. And if so, I know that the solution would be that function equals to a constant, the general solution to the differential equation. Okay, I need to check. So let me call this, I'm going to call this P, I'm going to call this one Q, as we have been doing. And then we know that, of course, if this is a differential of a function, then df, of course, is always partial f, partial x, dx, partial f, partial y, dy. So if this is the differential of a function, then q should be the partial derivative of f with respect to x, and p should be the partial derivative of f with respect to y. Okay. If that is true, then to Svar's theorem that we saw in the previous video, we need to have that the second cross derivatives coincide. That would mean, so if one is exact, then we have that p, let's write it, partial derivative of p with respect to y has to be equal, with respect to x, has to be equal to partial derivative of q with respect to y. All right. So if we write it in compact form, p sub x has to be equal to q sub y. All right. Well, let's compute them and check if this is exact. So first, let me compute px. All right. So if we compute px, we take this the derivative of the log. So do you remember how to take derivative of the log? You should from your previous course, right? But the derivative of the log is 1 over the argument multiplied by the derivative of the argument. This is applying the chain rule, well, Leibniz rule, right, if you want. Well, no, this is chain rule, not Leibniz rule, like that. Chain rule. So when you have you apply chain rule here, we get that this is 2x divided by x squared plus 1 for px. Okay? And q, how about q? Well, qy, it's equal, if I take it with respect to y, it's pretty easy, is 2x, this is the only term that contributes, divided by x squared plus 1. Oh, look how nice. They are equal. So that means that 1 is exact. All right, wonderful. So if 1 is exact, then we can now solve it with the techniques that we learned in the previous video. All right. Let's erase the board then and solve it. Okay, so we know that q is partial x, partial x, p is partial f, partial y, so we know now that q, of course, equals partial f, partial x, which is equal, we just copy q. This is 2xy divided by x squared plus 1 minus 2x. We can actually get to f through integration with respect to x. And if we do that, we integrate with respect to x. Now, integrating with respect to x, this thing is very easy because we have the derivative of the numerator, of the denominator in the numerator. Well, you remember your integration, right? Your basic integration. If we do that, the result of this would be y log of x squared plus 1. And this one is very easy because x squared divided by 2, so minus x squared. All right. But we know that the partial derivative with respect to x would have cancelled any functions of only y. So we need to add a function of y, an arbitrary function of y. Cool. Okay, so now we do the same with p. P is the partial derivative of f with respect to y. We just copy b from here. This is the log of x squared plus 1 minus 2. We get the function, so this is of course the function f of xy. We get the function f of xy through integration with respect to y. And if we integrate this with respect to y, this is actually pretty easy to integrate with respect to y because there's no y's anywhere. So the integral with respect to y is y log of x squared plus 1, and the same factor as here, as expected, minus 2y. Now again, the partial derivative of f with respect to y would have cancelled any functions of only y, right? So, of only x. So we add here the function, an arbitrary function of x that we don't know, okay? This is f of xy. Now, determining the values of those functions is very easy. By comparison, we get the common part, and then we see that the only function of x that should be in here is this one, and the only function of y that should be in here is this one. All right, so that allows me to pick one of the two expressions to write f of xy that we just found. F of xy, it's equal to y log of x squared plus 1 minus x squared minus 2y. Wonderful. That is not the solution to this equation. The solution to this equation, the implicit solution, is equating that to a constant. So we would have, remember the solution for this, if we integrate, so you have df equals 0. If you integrate the differential form, you get f of xy equals a constant. And then what we get here is that the implicit solution would be y that multiplies, well, I mean, I'm going to write as this and then we simplify it. Y log of x squared plus 1 minus x squared minus 2y equals a constant. This is the implicit solution. This is not the final solution to the problem, because the final solution to the problem requires you to solve for y if you can, and that's actually very easy because this one is linear on y, it's proportional, terms proportional to y only. So the solution, the explicit solution, y of x, what we want, right? We can get this solution by simplifying this a little bit. So we common factor of y, so y multiplies on the one hand the log of x squared plus 1, and it also multiplies minus 2, and then you have minus x squared equals a constant, right? We put everything that's not y on the right hand side, and then we find that y of x is equal to, and then we get c plus x squared divided by the log of x squared plus 1 minus 2. And this, my friends, is the general solution to the differential equation that we started with. So again, another example of exact equation that I hope settles better the knowledge that we had. This is maybe slightly more difficult to identify as exact. Perhaps you would have solved it as linear, it would have been fine, but it is certainly exact. We solved it as exact, and it worked pretty well applying the methods. All right, remember, any questions that you may have, you have to bring them on the in-person sessions. All right, let me erase the board and let's define a new kind of problem that we're going to face, which is exact equations that admit an integrating factor. So equations that are not exact but become exact after admitting an integrating factor. Let's erase the board and get to it. Imagine that we have an equation like this one. So that looks a lot like an exact equation, right? Let's say that x is the dependent variable and t the independent variable. Looks a lot like an exact equation, right? But then you go and check with the specific values of p and q, and you find that the cross derivatives of p with respect to t and q with respect to x do not coincide. That is not exact. So before abandoning all hope, it's possible that there's a trick to make it exact. Now, we have something equating to 0. One thing that I can do is I can multiply the left-hand side and the right-hand side by the same function, and the equation will still be true, right? Well, unless I multiply by very ill things. But in general, I can multiply the left and the right by the same magnitude, and the equation should still be true. All right. So, what if, let's write it. What if there is a function, let me call it mu of xt. Mu is a Greek letter, for those of you that haven't used mu a lot. It's the Greek letter mi, actually. We call it mu though. Mu xt, and there is imagine that there is a function, or what if there is a function mu xt, so that when I multiply this equation by mu of xt, pxt dx plus mu xt qxt dt becomes exact. So here I'm doing, what if I multiply the whole equation by something that makes this thing an exact differential form? How is that? All right. So let's see what would be the case then. All right, so then we know that this thing, this mu, let's call this thing p tilde, and let's call this thing q tilde now. And then if it's exact, we should have that p tilde derivative with respect to t should be equal to q tilde derivative with respect to x. If we expand this, what that means is that partial mu p partial t should be equal to partial mu q partial x. All right, so in general, so this is what has to happen in order for a mu to transform the original equation into an exact equation. Now, finding the mu that satisfies this condition, that's the condition that needs to be satisfied on the original equation, is in general difficult. But there are three cases that we will learn how to deal with in this course. Case number one is easy cases. All right, mu is only a function of t. I mean, not t always, right? What I mean by that is the independent variable, right? I mean, it's t here, but it could be x in a different equation and y be the dependent one. Another case that is easy is mu is only a function of x. Well, actually, what I mean by that, a function of the dependent variable. And the other one, mu is equal to some power of x, some product of x to the power of a and t to the power of b. Some product of powers of the independent and dependent variables. So these three cases, if you were facing in an exam, I mean, this course won't have an exam per se, right? But if you are solving problems and you find out one of these three cases, you're gonna have to, you're supposed to know how to solve it, and that's what we're gonna learn in the next whiteboard, all right? Okay, so let me erase the board and address the first two cases. Okay, so we had a formula here that we moved here and call it number 3, formula 3. So again, recall, equation 1 is not exact, but maybe there's a mu that makes it exact when I multiply both sides. And if that's true, this equation has to be fulfilled. Now, for the particular case that mu is only a function of x, things simplify quite a bit. If mu of xt is only a function of x, then equation 3 can be simplified. Because mu doesn't depend on t can come out of the partial derivative. So we get mu multiplying partial p partial t. And then this is equal to, and then we use the product rule or Leibniz rule, right? There's, the derivative of the product is the product of the derivative of the first times the second without derivative plus the first without derivative times the derivative of the second. So let's write that. So this is going to be the derivative of the first times the second plus the first times the derivative of the second. Now, little piece of advice. When you do this, Leibniz rule, of course, numbers, the multiplication of numbers commute, but sometimes you will have things that are not numbers. There will maybe be matrices or even infinite dimensional operators in a Hilbert space. So for those of you that may be interested in doing quantum stuff eventually, you're gonna have this issue. You're gonna work with objects that when you take derivatives and everything, you're gonna have to apply Leibniz rule, but they don't commute. The product of A times B is not the same as the product of B times A. Okay? So because of that, I always advise you to keep the order right. So Leibniz rule still works, but you need to keep the order. So if it's mu is first in both cases. Just a bit of advice. Of course, it's irrelevant for our case, but I think it's good practice to learn and create habits. All right. So if that's the case, we can actually solve for the partial derivative of mu with respect to x, and we find that the partial derivative of mu with respect to x, now I wrote total derivative here because I'm assuming mu is only a function of x, so partial and total derivative coincide in this case. So we have that this is equal to mu, and in the numerator we have partial p partial t minus partial q partial x divided by q. All right, so we find an expression for the derivative of mu with respect to x if mu doesn't depend on x. Now, for this to be true, for all this thing to carry, we can actually do an if and only if connection. And we know that, so here's the criterion to distinguish if this is the case. If, let's write this in simplified notation. If this thing, pt minus qx divided by q is a function of only x, then there is an integrating factor mu of x that is only a function of x. And not only that, we can find it. So let's call this equation 4 and let's solve it, because this is a differential equation and it's of the kind that we learned how to solve. It's separable. I can put the mu's on the left, the x's on the right, functions of x on the right. Of course, this is true if this thing is only a function of x, right? Which is this. So if that's the case, we find that, well, let's do it. So 4, I can write as d mu divided by mu equals pt minus qx divided by q dx. I integrate and I get a logarithm on the left, log of mu, right? And on the right I get the integral pt minus qx, whatever that is, dx. Now I can undo the log taking, of course, I can undo the log taking exponentials. And I'm gonna write, you remember you have infinite solutions, the general solution would have a constant. Here I just want one solution, one integrating factor. The integrating factor is not the final result that we want, it's a means to an end. It's a means that allows me to integrate the equation. So if I take exponentials on both sides, I get that mu of x is gonna be equal to the exponential of the integral of pt minus qx divided by q dx. There you go. And that is your integrating factor. So in practice, in an exercise, you are given an equation like that. If you want to check if it admits an integrating factor that is a function of only x, then evaluate this and ask yourself, is that a function of only x? If the answer is yes, it is, then you know, aha, I know an integrating factor and it's of this form, and you calculate it. All right? Good. Let's do the same, but when the integrating factor is only a function of t. Okay? Not just x. So let me erase the board. All right, so now it's the same case as before, but now mu, maybe there's a mu that is only a function of t. What are the conditions under which I can find that mu is only a function of t? And what would be the value of mu in that case? All right. So, same thing as before, equation 3, if mu is only a function of t, in equation 3, we can simplify because this mu comes out of the derivative with respect to x. So, what we get is, we apply Leibniz rule on the left, we get that partial mu, partial t, times p, plus mu, partial t, it's equal to mu, partial q, partial x. All right, if that's the case, same as before, we find that partial mu, partial t, that I wrote as total derivative because t is the only variable that mu depends on in this particular assumption, then we get that this thing is, in this case, q with partial with respect to x minus p partial with respect to t divided by p this time, and multiply all of it by mu. All right. So again, this equation, let's call it 4, it's a separable equation, same as before, and we can solve it. We get that d mu divided by mu equals qx minus pt divided by p dx. Integrating, I get that the log of mu it's equal to integral qx minus pt divided by p dx, and by taking exponentials on both sides, I find that mu of t would be equal to the exponential of the integral qx minus pt divided by p dx. Now, the condition for that to be true is that this thing has to be only a function of t, so let me write the condition. So if qx minus pt divided by p is a function of only t, right? That's the check. Then there is an integrating factor, only a function of t, and then there is an integrating factor mu of t with this form. Okay? So what you would check is this condition true? So I grab this equation, take p, take the derivative with respect to t, take q, take the derivative with respect to x, divide by p, check if that's a function of only t. If the answer is yes, then you know that you found an integrating factor that has this form. Alright, let's do an example and see in action. Let me erase the board. Alright, so we're gonna solve this equation. If we classify it, this is clearly an ODE. It's a first order ODE. It's nonlinear though, y squared and a 1 in here, so it might be a difficult equation to solve. Okay, let's see. Maybe it's exact. So the first thing we do when we see that is check for exactness. Okay, let's check. First we write it in the following form. We write it as a differential form. So we write x squared plus xy multiplied dy plus 3xy plus y squared multiplied dx equals 0. And then we call this guy p. We call this guy q. So now check for exactness. Check for exactness. So if we check exactness, to tell me that p derivative with respect to x should be equal, this is what we are checking, to q derivative with respect to y. Okay, let's check. So p with respect to x, it's equal to 2x plus y, and then q with respect to y, it's equal to 3x plus 2y. Oh, darn, they're not equal. So, not exact. If I asked you this question before this video, the answer would be, okay, I'm gonna go home, I don't know how to solve this. But, now you do. Maybe, I don't know. Maybe there is an integrating factor, an easy one, that makes this an exact equation. Let's try to find it. So, I'm gonna erase the check. We already know it's not exact. So we ask another question. Is there an integrating factor let's say it's only a function, let's say is there an integrating factor that is a function of x only, for example. Function, let's call it mu of x only, right? So that mu p plus mu q equals 0 is exact. A priori, we don't know if there is, and you could have checked y first, I don't know, but let's check first x. All right, so remember the criteria that we discussed to check. So if that's the case, then we know, well, yes, if, and then we write it here, q with respect to y minus p with respect to x divided by p is only a function of x. Remember, in the previous board we had q sub x minus p sub t, but it's the same as here, right? Because x was the dependent variable, now it's y, and t was the independent variable, now it's x. So this is on purpose in the example, so you see that the name we give it is not important. What is important is the role they play in the equation. All right, so let's check that. Okay, qy, let's write it again. Qy was 3x plus 2y, and dx was equal to 2x plus y. That correct? Yes. So if we subtract these two, we get that qy minus px is equal to x plus y. All right, and now we divide that by p. So qy minus px divided by p is equal to x plus y divided by p, and p is x squared plus xy. And oh, look at that, this is only a function of x, there's no y's in here, right? We win. I mean, I'm not laughing at the words, it's kind of a dad joke of math, so I'm sorry about that. This thing is certainly only a function of y. To see it, you just factor an x in the denominator, and then you get that this is x plus y, and then x multiplies x plus y cancels, and this thing is 1 over x. So that's why it was the joke, sorry. So the way I said it is just I wanted you to think, oh, but how come, if I don't give you a second to think, how come this guy is saying there's no y's? I'm seeing y's. Well, not really, it's an illusion. There were no y's. It's like magician, there never was a y. I was never wearing a t-shirt, kind of thing. All right, so now that we check, so we know, oh, there is mu of x that makes 1 exact. All right, wonderful. So what is the value? Well, we had a formula that we computed before. Mu of x would be the exponential of the integral with respect to x of qx minus py divided by p dx. And we've already computed what it is. This is it's going to be the exponential, all right, of 1 over x integrated, right? So the exponential of 1 over x dx. But look how easy that is, because the integral of 1 over x is the log of x. So this is the x of the log of x. I'm going to write the absolute value because I'm going to pick one solution, so it doesn't matter. So the x log of x cancels, and this is just x. So we found an integrating factor, mu of x equals x, makes this an exact equation. Let's implement it and see it. Let me erase the board and implement it and finally solve the equation. All right, so we multiply equation 1 by x, which is the integrating factor, and hopefully that means that we have an exact equation if we did the math right. Let's see. So this would be x multiplying, so I'll just write the whole thing, x cubed plus x squared y, this goes with the y, plus 3x squared y plus xy squared. That goes with the x equals 0. Now we call this guy p tilde, we call this guy q tilde. And let's do a quick check for exactness. I mean, it has to be, we did the math right, but let's make sure that this is an exact equation. All right, so if this is an exact equation, so maybe check, I'll write it, for exactness. All right, so p tilde with respect to s should be equal to q tilde with respect to y. Let's see if that's the case. P tilde with respect to x is 3x squared for the first term, and then 2 plus 2xy. And then if we do q tilde with respect to y, this is easy, 3x squared for the first term, and for the second term, just with respect to y is 2xy. Oh, look at that, they coincide, and it is exact. How cool is that? We had an equation here that was equated to 0 was not exact. Because it's equated to 0, I can multiply both sides of the equality by whatever I want and keep the same equation. In particular, we multiply by x. And after multiplying by x, it becomes this, the same equation, look at that, we just multiply by x. So, then it became exact. And now I can solve it as an exact equation. Let's do it because we need to get to the final result. All right. So let's treat this thing as an exact equation and solve it. And how do we do that? Well, we know that this p, of course, is going to be the partial f with respect to x, with respect to y. This q is going to be the partial f with respect to x. All right, it's multiplied to dy and the dx. And just for reminder, df, the differential of the function, now that we know it's exact, is partial f partial y dy plus partial f partial x dx. All right. So we have, let me write this here, dy, partial f dx. So we have here that partial f dy is equal to x cubed plus x squared y. We find the f of xy through integration with respect to y. So we know that f of xy then is equal to the integral with respect to y of x cubed plus x squared y dy. And that is easy. That is x cubed y and then plus 1/2 of x squared y squared. Of course, the partial derivative with respect to y would have killed any functions of x, so we need to add an arbitrary constant that in this case would be a function of only x. Alright, we do the same with partial f with respect to x. In this case, this is 3x squared y plus xy squared. So through integration with respect to x now, we find f of xy, which is the integral of 3x, yeah, that's right, 3x squared y plus xy squared dx. And we do it, this thing is going to be x cubed y, nice, same term. The terms that contain both should appear in both, plus x 1/2 of x squared y squared, plus of course a possible constant that depends only on y, because the partial derivative with respect to x cancels any function of y. But we see by comparison that we have both in both cases. There are no, so we know for this comparison that hx equals dy equals 0. There are no extra, because any function of only x should have appeared here. Any function of only y should have appeared here, and they're not, they're 0. So we found the solution. The solution is that, well, the f such that the equation is the differential of that f is 3x squared y plus, oh sorry, I'm copying the wrong thing, x cubed y plus 1/2 x squared y squared. Wonderful. This is not the solution to the problem. The solution to the problem is, well, now I need to write f x y equals a constant. That's the solution to the problem of integrating a differential form. If you have the f equals 0, then the solution is, this is the differential equation, right? Then the solution is that f of xy equals a constant. So we write the solution, the implicit solution, as 1/2 x squared y squared plus x cubed y equals constant. And that is the implicit solution. Of course, I haven't finished here because this is not enough. When you can do it, you can solve for y and get the explicit solution. You can have y of x. This is very easy, it's a quadratic equation. So I'll just write the result and you substitute on your own in the quadratic formula.
Alright, so through the magic of crappy video editing, here is the solution, the explicit solution. This is obtained, of course, from the implicit solution that I translated into, that I copied into the first line here. And then using the quadratic formula, we solve for y and simplify a little bit. Okay, so we have seen how to solve an equation that wasn't exact, but became exact when we multiplied by an integrating factor that depended only on the independent variable. So now, what is left for us to do is to see an example of the other case where the integrating factor is actually a function of the dependent variable instead. And then one more example that will be a case when the integrating factor is a product of powers of the dependent and the independent variable. And with that, we will conclude this video. All right, so let's get to it.
So let's erase the board. All right. So we're gonna see another example. In this case, we're gonna find an equation that is gonna become exact after multiplying by an integrating factor that will be a function of the dependent variable rather than the independent variable as before. Now, this is what you will be given. This is the equation. Derivative of y equals x plus y sine y divided by x sine y plus cosine y. And then you look at that, you classify, and you say, oh, it's an ODE, only one dependent variable, which is x. The independent variable is x, the dependent variable is y. Right, very nonlinear. There's a sine and a sine and a cosine. Oh, that's very nonlinear. Maybe difficult to solve, but perhaps it's exact, you may think. So then you write it as a differential, or, you know, less rigorously speaking, you write this as dy dx, and then dx times that way and that again, a non-rigorous way of talking about it. You write it as a differential equated to 0, differential form equated to 0, and then you say maybe this is exact. Maybe it's an exact equation, so you check for exactness, and then you say, okay, maybe q with respect to y. Let's compute that one. We use the Leibniz rule, product rule, for that. So the first term, the derivative is 1, so the first term is sine of y, and the second term is the cosine of y. So that's the derivative of q with respect to y. And then you say, okay, what is the derivative of p with respect to x? So the derivative of p with respect to x, that's very easy, it's just the sine of y. And we see that it doesn't coincide, so this thing is not exact. All right, maybe we can find an integrating factor. Maybe we can find an integrating factor that depends on x. And I can tell you already, you won't. There isn't any in this case. So you would try and you would find that there isn't. But, and actually it's a good exercise. I encourage you to try to find it. Check the condition to see if there is one, and make sure and convince yourself that there isn't one. Now, let's see what happens if we try to find an integrating factor with respect to that is only a function of y. So the question is there a mu of y such that mu q dx plus mu p dy equals 0 is exact? All right, and then you know the answer. The answer is yes, if p with respect to x minus q with respect to y divided by q is a function of only y. Notice that in the when we define it and we said it, the dependent variable, we call it x actually, and the independent variable we call it t. Here, the dependent variable is called y, and the independent variable is called x. You see, so this done on purpose, so you get familiar with identifying dependent and independent and being able to not just mindlessly apply a formula, but knowing what you're applying when you apply it. You know, machines are really good at applying formulas. You don't want to be substituted by a machine so early in the 21st century. All right, so let's check, right? Let's compute these things. So we had, again, p with respect to x, that's easy. That's just the sine of y. Q with respect to y, that one is x plus y. Well, I'll do first the first term, which is just sine of y. And then plus x plus y cosine of y. So if we write this, px minus qy divided by q, what we get, p, the sine and the sine, well, I'll write it, the signs cancel, sine y minus sine y, these are going to cancel, minus x plus y cosine of y, and this is divided by q, and q is x plus y sine of y. Nice. So this cancels, and one did that cancel, this thing cancels with this one as well. So the result is minus cosine of y divided by sine of y. How nice. This is only a function of y. Nice. So the answer is yes. There is a mu y that allows me to integrate, that makes one exact. Wonderful. So now we have a formula that tells me what is the value of that integrating factor. Let's apply it. So that formula told me that mu of y is equal to the exponential of the integral of px minus qy divided by q dy. All right, so that's simple because it's the exponential of the integral of, well, I'll take the minus sign outside, exponential of minus the integral of cosine y divided by sine y dy. And that integral is one of the immediate integrals that you've studied. You have 1 over a function multiplied by the derivative of the function. So that's a logarithmic derivative. It's a logarithm, I mean, not logarithmic derivative. This thing is the exponential of the minus log of sine y. I'm not writing the absolute value bars here because it's unnecessary for what we want. We want one integrating factor, and we can use one branch for positives and one branch for negatives, so it's fine. We can actually not write it here, there's no problem. If you want, you can write it, doesn't change anything. The nice thing about it is that the exponential cancels the log. Well, I can do, let me just write this as 1 over e to the log of sine y. All right, the minus is my exponent is negative, so I put in the denominator, and the exponential cancels the log, and the integrating factor I find is the sine of y. Wonderful. All right, so I found an integrating factor that is a function of y in its explicit form. Let's now apply it and make sure that it makes the equation now an exact one. Let's erase the board. All right, so the integrating factor that was here was moved here now, and I multiply 1, the equation 1, by the integrating factor, and I'm left with this new equation, new differential form. That is equivalent to that equation because I multiply both sides of the equation. All right then, so let's check that this is actually exact. Easy, right? Because for exactness, I check exactness. How do I check? Well, q tilde with respect to y, this thing is 1, should be equal to p tilde with respect to x, that if you can check there is also 1, two things coincide. It is exact, so we made the equation exact. Wonderful, let's solve it. Now, how do we solve it? Well, because it's an exact equation, now we know that df, this equation, so let's call it 2 is of the form df equals 0. So this is the differential of a function. And we know that the df is the partial with respect to the partial of f with respect to x dx plus the partial of f with respect to y dy. All right, so this thing we identify with the q tilde, this thing we identify with the p tilde, and then we can write that partial f, partial x is q tilde, which is x plus y, and then partial f, partial y is p tilde, that is x plus cosine y divided by sine y. All right, now integration with respect to x here gives me f of xy, which is equal to, integrating with respect to x is really easy. I'll do it in one go. Well, maybe I'll write it. X plus y, I'll write it for this time, dx, which is equal, again, which is equal, plus a possible, I'll write it here, plus a possible constant that may depend on y, because again, the derivative is partial with respect to x. And if we do that, we get x squared divided by 2 plus yx plus a possible constant, quote unquote, that may depend on y. Wonderful. Let's do integration with respect to y here. That gives me also f of xy, right? And then by integration, we get the integral of x plus cos y sine y dy. That's very easy. The first one is just xy. And the second one, remember, this is the integral of a function, 1 over the function times the derivative is a logarithm of the function. So this is the log of the absolute value of sine of y. All right. Plus, of course, I mean, I didn't write it here, but it should be a g of x here. And of course, there's a g of x here. There's a constant of integration that may depend on x because we took the partial derivative with respect to y before integration. All right. Now, we identify the missing functions really easily. This one is this one. As the function that only depends on y that is here, it has to be here, and that's the only one that doesn't depend on x, only on y. And also we identify the function of strictly x, that is here. All right. Screwed up the sign, sorry. All right, this is a plus. Okay, so now we found the form of f. We found that f of xy is x squared divided by 2 plus xy plus the log of the absolute value. I'm going to need to write the brackets. The log of the absolute value of sine y. All right. Many people would box that as the solution. That would be wrong. Marks would be lost if you do that. Remember that the solution, because the equation is of the form df equals 0. Df equals 0 is equation 2, right? So the solution to the equation is integrating both sides, f of xy equals constant. So let's write that. F of xy, which is x squared divided by 2 plus xy plus log sine of y equals constant, is the implicit solution to the equation. That's what you box, that's the solution. Usually you need to solve for y of x. In this case, it's impossible. This is a transcendent equation in y, so there's no way to solve for y if you want, isolating a simple closed expression. So we just give the implicit solution as the solution. We solve the differential equation. All right. So now we've seen how to solve an equation with an integrating factor, the examples that depends on the integrating factor depends only on the dependent variable. And we saw previously one case in which it depends only on the independent variable. There's only one more thing to go. That is integrating factors that depends on products of powers of both variables. Let's see that now, and that's the last part of this video. Let's erase the board. All right, so here's the problem that we're going to solve. We're going to demonstrate how to do that with an example. Find the general solution of this equation. You will be given that, and you will be given with an integrating factor of the form xayb. So that would say that's what you will be given. And then that probably means that this is not an exact equation and requires some integrating factor. And you need to find it. And it's going to be of this form. These are the hints that are given to you. All right. First, let's check if it's really exact. Maybe I'm just trying to con you. It was exact all along. Let's see. If you write it as an explicit differential from equal to 0, we get that. This is what we call P. This is what we call Q. All right. P usually called the one that goes with the dependent variable, and Q the independent variable. So let's check exactness. Q with respect to y, it's equal to 10xy minus 2. And then P with respect to x is 6xy minus 1, certainly not the same. So the equation is not exact. What a surprise. All right then. But the exercise also tells me that maybe there is an integrating factor that is of the form of x to some power times y to some power. Okay, let's see. So that means that would mean that if I multiply mu times q dx plus mu times p dx, then that thing equals 0 is exact. Right? I'm adding this to the phrase. With an integrating factor of the form x to the a, y to the b means that integrating factor makes this equation exact. So what we do is now we multiply this equation by mu and see what we get. So multiplied by this mu, we get for this factor 5x to the a plus 1, y to the b plus 2, minus 2x to the power a, y to the power of b plus 1. See what I'm doing? dx. I'm multiplying this thing by this. So x to the 1 times x to the a, x to the a plus 1. Y squared times y to the b, y to the b plus 2, and so on. That's what I'm doing. Plus, and then the other term will be 3x to the a plus 2, y to the b plus 1. Right, there we go. Minus x to the a plus 1, y to the b, dy equals 0. So this now, it's my, well, I'll put it on top. This now is my q tilde, and this now is my p tilde. All right, so if the equation is exact, remember now, q tilde with respect to y should be equal to p tilde with respect to x. All right, so let's check. So q tilde, I'm gonna write both like this, one on top of the other. Q tilde with respect to y is, all right, b plus 2 comes down, so I have 5 times b plus 2, x a plus 1, y b plus 1. All right, minus, now this one with respect to y again gets a b plus 1 down, 2 b plus 1, x to the a, y to the b. All right, and then we get that p with respect to x would be equal to, now I get 3 times a plus 2, x to the a plus 1, y to the b plus 1, minus, and I get from this one an a plus 1, x to the a, y to the b. All right, so I need to find the factor, I need to impose that these two things have to be equal. So if these things are equal, they have to be equal, like imposing equality for all values of x and y. Remember that symbol means for all values. So for all possible values of x and y, they have to be equal if this is an integrating factor. So I impose it to find a and b. A and b are my unknowns. So I impose that they're equal, and if they're equal for all values of x and y, the only way they can be equal is if the coefficient of x to the a plus 1, b plus 1, in both cases is the same, and the coefficient of xa and y, x to the a and y to the b is the same in both cases. Otherwise, there's no way they would be equal, because there are different powers. They need to be equal coefficient by coefficient. All right, that gives me 2 equations for the 2 unknowns. Let's equate these 2 coefficients. So first coefficients of x to the a plus 1, y to the b plus 1. That gives me the following equation. Equating the 2, I get 5 times b plus 2 equals 3 times a plus 2. All right, wonderful. And then I also get another equation with the coefficients of x to the a, y to the b in that equation. That means that this has to be equal to that. The minus I don't write because minus in both of them, so twice b plus 1 has to be equal to a plus 1. All right, this is a very simple system of 2 equations. Then we can check by eyeballing it, even though it's simple to solve, but you can even eyeball it, that b is equal to 1 and a is equal to 3. How is that? Because look at that. 3 plus 2 is 5, 3 times 5. 1 plus 2 is 3, 5 times 3, so it's 15 equals 15 with these values. And here, 1 plus 1 is 2, times 2 is 4, and 3 plus 1 is 4. So this one you can eyeball and solve. If not, just solve it. It's arithmetically super simple, right? So we found our solution. That means that, yes, nice, we found an integrating factor mu of xy that is equal to x to the a, and a is 3, x cubed, times 1 to the 1 times 1. This is my integrating factor. Look at that. Who would have thought that there's an integrating factor like this that makes this exact? All right. Final step in today's video is solving the equation. So let's erase the board and transport this integrating factor here. All right, so transporting the integrating factor here, now with the values substituted for a and b, we multiply and we get, this is going to be, after multiplication, is 5x to the power 4 y cubed minus 2x to the power 3 y to the power 2 dx plus, we have here 3x to the power 5 y squared minus x to the power 4 y dy equals 0. And this is here, this is my q tilde, and this is my p tilde. Let's quickly check that we computed it right. Let's check that this is actually exact. So if it's exact, q tilde with respect to y should be equal to p tilde with respect to x. Let's check. Q tilde with respect to y is, okay, that's a 15, x to the 4, y squared, minus this with respect to y, so a 2 comes out, so it's a 4, x cubed y. All right, let's compute p tilde with respect to x. So that takes down a 5, so it's a 15, x to the 4, y squared. Well, so far so good. And the other one takes a 4 down, x cubed y. Nice, wonderful, they are the same. So, it is exact now. How is that? All right, let's solve the equation. So, let's solve the equation, because now that it's exact, we know that equation 2, let's call this one 2, equation 2 is of the form df equals 0, where remember that df is partial f partial x dx plus partial f partial y dy. All right, nice. So this thing is gonna be our q tilde, and this thing is gonna be our p tilde. All right. So we just write the equations here. Partial f partial x is equal to 5x to the power 4 y cubed minus 2x cubed y squared, and partial f partial y it's equal to 3x to the power 5 y squared minus x to the power 4 y. All right, let me erase that now. And then here we can integrate with respect to x. That gives me, that's nice, the 5 cancels, right? I'm going to do it directly because this is integrals of polynomials. So the first term gives me an x to the 5 divided by 5, that cancels the 5. So it's x to the power 5 y cubed minus this one, when I integrate with respect to x, I get a 4 divided by 4, so it's minus 1/2. And then we get x to the power 4 y squared, plus of course a possible constant that can depend on y. All right, let's do it. Let's integrate this one with respect to y. Oh, by the way, this is of course f of xy. Here we also get f of xy with that integration, right, of the partial derivative. But in this case, integrating with respect to y, the 3 cancels again, which is nice. So it's x to the 5 y cubed, wonderful, that coincides. Terms that include both terms, x and y, should appear in both. And this one, with respect to y, is a 2 divided by 2, so minus 1/2 x to the 4 y squared, plus a possible function of x in this one. Although we see, this is f of x, because of that I'm comparing, we see that there's no terms missing here, depending on y, that should be here. There's no terms missing here, depending on x only, that should be here. So we know that h of y equals g of x equals 0. And then the function f of xy is just x to the power 5 y cubed minus 1/2 x to the 4 y squared. That's not the solution. Remember the solution, because the equation 2 is df equals 0. The solution to 2 is integrating that is f of xy equals constant. All right, so let's write that. That's the solution. That would be a very stupid way of losing marks, right? Not writing this. To the cube, minus 1/2 x to the 4 y squared equals constant, and I squared. That is the solution to the problem in implicit form. Now, this is a cubic equation. In principle, you can solve for it. Just solve for y as a function of x. You can do it, that's no problem. But if it's a cubic equation, it's fine. If you don't, if you leave it in implicit solution, it's totally fine. All right. Okay, so now you've seen how to find integrating factors that are products of powers of x and y. And these are the 3 cases, like only a function of y, only a function of x, or a product of powers of x and y, are the only 3 cases that I will ask you to compute an integrating factor for exact equations in this course. So this ends exact equations, and we're gonna get to the final part of the first block of the course, that is linear first order equations. You're gonna learn how to solve any linear first order equation before moving to something else. All right, thank you, and I'll see you in the next video.